Okay, class number 38 starts on page 351, and we will talk about rotational energy conservation. So the conservation of energy principle that we learned earlier also applies to rotational objects. And this is the equation we had. Delta K plus delta I plus delta IF plus delta UG plus delta UE equals to work done plus heat transfer. And now we're going to make some changes. So we need to also show the emphasis on the rotational one, right? Because there is also rotational energy. And so what we need to do is we need to split delta K into two delta Ks. Okay, so one is going to be for translational, the other one is going to be for rotational. And here you can see that we are doing that. Delta KT is 1/2 mv squared, and plus delta KR, and KR is 1/2 I omega squared. And the rest is the same. The order doesn't matter if that confuses you. Like I usually write down delta U's first, then delta I's, but it doesn't really matter. You're just adding them up. And the important thing here is now we have two forms of kinetic energies, and we need to also split the kinetic energy term into two, okay, for the rotating objects. And so if we also investigate the work done by the rotating for a rotating object, we can consider this system and analyze that. So we seek the work of the force F, which causes the disk to rotate. So far, like we used, for example, tension force as the force that's causing the rotation. But again, just label it general. Let's just say it's F. And then so you can see that F is not tangential. Okay, so first thing you do is kind of split the components as we did before, FR and FT. One thing is this is the pivot point it's rotating from its center, so the moment arm is from this pivot point to the force point, that is R. And so what we need is the force components, one along this radial distance, and the other one is tangential. Okay, so those are FR and FT. So the force Fr is perpendicular to the displacement and it does not do any work. Okay, the displacement is gonna be along this arc, right? And after a very short time interval, the force will have caused the disk to rotate by a small angle, okay, d theta. So we're thinking infinitesimally small changes first. And the distance traveled by point P, it was right here before, right now it's there, over this interval will be the small arc length, ds. Again, as I showed it earlier, it's like right here. It's going to go from here to there, and this is what we call as ds, okay? And using the arc length equation, S equals to r theta, you can also write infinitesimally small arc length. So it becomes ds equals to r d theta. Because r is constant, the differential is going to be on theta, so it's d theta. And kind of keeping that on the side, and knowing that ds is our displacement for this, like since we are going to calculate work done. And the small amount of work done as a result of this movement would be dW, right? So you're putting that d again because it's a very small amount of work due to a very small amount of displacement. And just like we know before, assuming this force is constant, we use work done equals to F dot D. So this is our equation to use. And if we already know that FR does not do work, right? Due to FR, work is 0, so we're focusing on the tangential components. So when you think about that, then F dot D becomes FD cosine theta. F is FT. And D here is the displacement, so it's our ds. And cosine theta between them is always 0. okay? Because like when it moves, that tangential force is always tangential to the arc length. So the direction and ds is also tangential for that instant. That means they point the same direction. So the angle is going to be 0 for that reason. That gives you cosine 0 to be 1, and that is ft/ds. Okay, and next you're going to plug it in what you know for ds, and that is rd theta. This becomes ft/rd theta. Okay, and that is the small amount of work done by that force. So what is ftr? That is the torque due to that tangential force, right? It is actually torque is equal to ft, so r times ft times sine theta, but again, the angle between those two is 90, so sine 90 goes to 1, so it becomes only ftr, and again, this is torque due to this tangential force. Okay, so you're replacing that with tau, as you can see it here, and d theta multiplied, and we simply again use the work definition, and this is what we get. dw, I'm gonna write it here, this is the small work done, equals to torque times small displacement, right? So this is also done. To get the total work, we have to integrate, because again, this is infinitesimally small work due to infinitesimally small displacement. What about the total work, right? So you integrate both sides, and then the w becomes w here, as you can see it, and if torque is constant, tau comes out, and the d theta is only from initial to final, and you simply get this answer, right? But if tau is not constant, it's changing, then you would have to integrate, and now you need to write the tau in terms of theta, then you have a theta function to integrate. But if you assume that, or if it is known that torque is constant, then you simply have work done to be the torque times the displacement, okay, but angular displacement, which is very similar to what we did in the translational motion, okay, force times displacement, right, final minus initial x, if it was 1D. So there's there's still similarities. You can still kind of use the mapping to figure things out, but there are also very important concepts that you need to understand when to do an integral, how to do an integral, why did we use work done is equal to force times distance, for example. There are conditions, as you remember, to those equations as well. So let's kind of keep everything in mind, what we learned, because we are building on top of that in this chapter as well.